All right, good morning, everybody. Just to check, can everybody see and hear me? It's a new week. I've had some technical difficulties. I had to restart, so I'm just paranoid, like always. All right. Hopefully, everyone had a nice extended weekend. Since Friday, we didn't do too much. Um, if there were any issues that you noticed with our practice pop quiz um, procedure that we can improve, let me know. But it's more just practicing on your end to see if you can scan and send and do everything in time for the more important quiz and final exam. But let me know if there are any issues. All right, so we ended Thursday, which is it's a while back, with the truncated or the truncation concept. And we said this can be much easier if we know our platonic solids very well. Where are the platonic solids? Up here somewhere. There we go. Those guys. Which means if I'm going to truncate the cube, doesn't matter if my webcam is in front of it right now, if I'm going to truncate the cube to get a new polyhedron, I better know exactly how the cube works. I don't have to have a perfect picture because I'm not relying on the picture that much. But I do need to know how many faces does it have, how many vertices, how many edges, how am I going to figure it out if I'm not memorizing it, which I'm not really. Can I get those numbers? Because when I truncate, I need to know, okay, what is that action doing to the cube and how does that affect my numbers to get the face, vertex, and edge numbers for the truncated cube, for example. And we discussed the truncated cube we see here with its new faces, but we have to be able to truncate each of the platonic solids. So eventually you need to practice this process for each of them. I know in the problems, I think the one question is asking for the truncated octahedron. You have to practice all of them, even if they're not specifically listed in the problem questions. We will build up to the more complicated ones by starting with the truncated tetrahedron. So let's get that going. As a side note, before I forget, if you have a question you want to ask, but you don't want to interrupt, you can totally put a little raise your hand emoji in the chat like this. And then I know to ask, because I think many people um, don't want to say anything out loud for fear of interrupting, but that's never going to be an issue. Feel free to interrupt me as much as you want. We have a lot of time to discuss all of these things, and I know especially truncation is not the easiest thing for everyone. So say what you need to say uh, to get on top of this. Any questions before we begin? Okay, I guess not. So let's start by drawing a tetrahedron. Let's just say what we're going to do. We're going to truncate, whoops, truncated tetrahedron. Messy writing, but it's still okay. So first, I need to know the tetrahedron. My sketch doesn't have to be perfect, but in this case, it will help to have a sketch that's clear in one vertex at least. All the vertices are the same, so if I can just have my sketch to clearly show a vertex, the rest of the diagram doesn't have to be perfect. So for the tetrahedron, I I have to draw it first to help myself. And I'm going to draw it this way so that I can see a vertex. The other way with the triangle facing me and the dots at the back, dotted lines at the back is not wrong, but it doesn't help me to look at the back as easily. So I like a front-facing vertex to work with to figure out what happens in the truncation. So this version of the tetrahedron is maybe a little bit nicer. So now, before I bother with truncation, I need to remember faces, vertices, edges. Faces, it's in the name, 4. Now I memorize as little as possible. I pretty much memorize nothing, to be honest, because the faces, the face number is in the name. No memorization required there, other than understanding the Greek words. Vertices and edges, I'm certainly not memorizing them at all. So I need to calculate the vertices again. Now for this simple shape, sure, you could just count them 1, 2, 3, 4. There's so few of them that there's no calculation needed. But for the harder ones, I'm not confident in my memory. So how did that calculation go again? Well, I have 4, let's say here, 4 triangles because 4 faces and the faces are triangles. So that means my vertex contribution is 4 times 3, 4 times 3. All the vertices that these faces contribute, that's 12. And how many faces come together in a point? 3. So that gives me my 4 vertices. Let me just put this over here. And we've done that. Go look back at the video, detailed table and everything. We're just doing that quickly again. If you take this route, of course, you can take the route of blind memorization. There's nothing wrong with that. I just don't trust my memory, especially under pressure. Edges. Again, the shape is simple enough. I can count them 1, 2, 3, 4, 5, 6. Or I can use Euler's formula, faces plus vertices equal edges plus 2. So my left side is 8, which means the edges number has to be a 6. All right, so once I have these 3 numbers for my platonic solid, then I can worry about truncating it. Then the truncated version of the tetrahedron. And I'm going to try and figure out what are the faces, what are the vertices, what are the edges. All right. So now I'm not going to draw the truncated tetrahedron completely. That's going to be messy and difficult, and it's going to look like this. That's a truncated cube. Drawing that, it's not going to play to my strength. Truncated tetrahedron, whew, it's not even the simple one, not the easiest one to look at and draw completely. It's maybe not impossible, but that's not the goal here. The goal is to simply get the properties and understand what is happening to the tetrahedron. So if I cut off this bottom vertex, I cut it off at the back as well. What did I now create? What happens at every vertex is exactly the same, so I just need to focus on one. So now this corner point is gone, and I've cut it off to create a triangle. So I have new triangle faces, the same as the vertices. So I have 4 triangle faces. I don't know how we should write this. Let's say here 4 triangle faces. But I also have, when I cut this off, at every vertex of the original tetrahedron, now I'm making them smaller than they actually are. What do I have in here? I have a hexagon. So I have, for each original face, of which there were 4 as well, I have hexagons. 4 hexagons. It doesn't really look like a hexagon. It should be regular, but I don't want to cut too deep into the corner. So I have 8 faces in the truncated tetrahedron. Again, stop me if I need to repeat anything or anything happens. For the vertices, I need to now think, well, I originally had these 4 vertices in the tetrahedron. Now I cut them off and created little triangles in their place. Each triangle has 3 vertices. So my original 4, the same as this one, is now multiplied by 3 to give me 12 vertices in the tetrahedron. All right, and then the edges, not much to think about. I use Euler's formula, faces plus vertices equals edges plus 2. Let's just finish this. Faces and vertices together, 20, which means edges has to be 18. I'm not going to count them. Where did I get the 3? I'm assuming this 3. 3 because I now create 3 new vertices. When I cut it off, I create a new triangle face. And in doing that, I've created 3 vertices in my truncated tetrahedron instead of the 1 vertex in the original tetrahedron. And because originally there were 4 of these corner points, each one now becoming 3, it's 4 original times 3 gives me my vertices for the new truncated tetrahedron. So you can see how and why we need to go really slowly and have a decent diagram to work from to help me visualize what's happening here. But it's still the case that my new numbers come from the original Platonic solid. Any other thoughts on this one? Right? Silence means complete understanding and agreement, of course. Then you can work on truncating the other ones. We're not going to do them all here, but we can easily do them in an office hours session. Next up, I'm just going to leave it like this so the webcam doesn't block anything. So we had the truncated concept. Now, where did this come from? It came from the fact that in the Platonic solids, we had the very strict requirement that everything's regular and there's only one face for, there's only one polygon to use as the faces. Then we relaxed that by allowing more than one type of polygon to be faces of my polyhedron. Still regular, still regular, but I have more options now. So for example, the truncated cube is a polyhedron with, I guess we can call it semi-regular in a way, with regular octagons and regular triangles, but I have more than one type. And again, remember that we have an hour after this to discuss more specifically any issues. Uh, my goal right now is to maybe just get a big picture of these more complicated shapes, and it's the last thing we have to do. And then we can open it up for questions, any questions specific people have. For example, the cube, we know that the cutoff of the vertex is a triangle because of how many faces there are that come together in the cube. Because three square faces come together, when I cut off the vertex of the cube, I'm creating this yellow triangle. It's a triangle because three faces originally came together. So when we practice the other Platonic solids with different numbers of faces coming together, we'll see cutting them off creates a different shape, but it's based on how many faces come together, which is a property of the Platonic solid, which again is why I need to know my Platonic solid super well before even bothering with truncation. Okay, now there are other, so I can think of it in different ways. I can think of it as building from the Platonic solid to create these more general polyhedra. And I can create something in a way that truncation can't. Now, I will lead in by saying this one is far less important. It's just being aware that there are other things than truncation. These are called snub polyhedra. If I start with my familiar cube again, what happens is I pull the faces apart, pull them apart with gaps in the middle. So the red one's up here, the side red one is further out, the front facing red one is further out. I pull them apart, all separated. Then if I fill in those gaps to create a solid shape, I have these yellow and blue squares and triangles as the gaps between them. Now that itself is a new polyhedron that we'll see again. Then I can go one further by rotating the sides by a little bit. And what that does is change the square yellow faces into two triangles. And I have this snub cube. So this process, of course, is much more complicated. The only goal I have is to know that these things are out there, and you can, in your own time, examine and explore them further. Truncation is our focus, but know that that's not the only thing one can do to the platonic solids to create more complicated polyhedra. So we just want to be aware of it. Okay, so we have these three sort of steps, and they all are these semi-regular polyhedra in that their faces are regular polygons, but it's more than one type, and I have some variations. So that's all I want to know, that there is something other than truncation to create these shapes. So deep, calming breaths when I look at snub polyhedra. I'm not going to look at it in detail or figure out anything like I did for truncation. What we can do for any of these polyhedra, the platonic solids, the slightly fancier ones, really any of them, they all have the property, regardless of how complicated they look, they all have the property that each vertex has exactly the same things happening around it. The same kinds of faces in the same order come together to form a vertex of this polyhedron. In the case of the snub cube, I can look at any specific vertex. The one right in front of me, looking at me, has a square and four triangles coming together. If I just isolate that, I'm not sure what the little white line is doing there. This is my vertex. One of them is not blue anymore, the triangle. It's now, they're all yellow. I have a square and I have four triangles. I can represent what is happening to this shape completely, defining the shape by way of its vertex figure name. By picking a vertex, picking a starting face and going all the way around. So for example, here I've picked this bottom yellow triangle. That's a 3 because it's a triangle. Then the blue one is a 3. Then the next yellow one is a 3. Then a 3. And the red square is a 4. So the vertex figure name of the snub cube is 3, 3, 3, 3, 4. Again, just showing that it doesn't have to be a simple um, platonic solid. The vertex figure name defines what is happening to the semi-regular polyhedra as well, because they all have the property that every vertex is exactly the same. All right. Now, these other convex semi-regular polyhedra, the truncated ones, the snub ones, they all form part of a group called Archimedean solids. Now, Archimedes uh, went out and found all the semi-regular polyhedra you could possibly make, and it turns out that there are 13 of them. Not that much, but by allowing, just like for the tessellations, we had just three regular tessellations, and then when we opened it up to semi-regular, we had 8 possibilities. So just like this, we have 5 platonic solids. When we allow more variety in the faces, we now have more shapes. Archimedean solids, one group of that, and you can make 13 of them. So if I just go to Wikipedia and look, or I just Googled it, look at Archimedean solids, there are many pictures listing all 13 of them. I'm not going to bother memorizing them all, understanding them all. Some are much more complicated than the others. I just want to highlight the snub cube is one of them. The truncated, bottom left, truncated tetrahedron is one of them. I can truncate an octahedron. I can truncate a cube. I can truncate other things, and it gets a little fancy. I can truncate the icosahedron. They are all part of this larger group of Archimedean solids. Truncation isn't the only thing. There are others, but Archimedes proved that there are only these 13, and you can't make anything else with regular polygons as faces while still having a convex, roundish shape. So we just want to know how many Archimedean solids there are, and do you know a couple of them? And by focusing on the truncated Platonic solids, we have some of them already. So there's no need to worry about the fancier ones, but you can explore that further if you are very curious. Any questions on what we need to know for a test question? I think that is the main concern, perhaps.
Yes. Do we need to know any of those ones for the test?
So you need to know how many there are,
Okay.
and can you give an example of, let's say, two of them?
An example, just a name, or do you want us to
Yeah,
be able
just
to?
the name, just the name.
Okay.
But by focusing on the truncated polyhedra, those are in this group. So you've already done that.
Okay. And then with the snub polyhedra, do we need to also just know that that's an option, or should we know more about that too?
Nothing more than it is an option. It is part of this Archimedean solids group.
Gotcha. Thank you.
All right, so focus on the truncated, put effort into truncation, and we'll have a lot of time to figure it out, and eventually we'll do them all uh, after we've finished this chapter. So if even if you are completely confused about how to get the truncated um, Platonic solid numbers, we can still understand this next grouping of shapes, which are called the Archimedean solids. And we'll eventually figure out truncation, and those truncated polyhedra are a part of this group of 13. And Archimedes showed that you can't have any other than these 13. But unfortunately, it doesn't end there. We, with our semi-regular polyhedra, we have these Archimedean solids, but we also have two other groups. They're not as complicated as the Archimedean solids, but they are also technically semi-regular polyhedra, and they are the prisms and the antiprisms. Now, in elementary school, the concept of the prism is introduced fairly early. What would you say is a prism? Yeah, don't worry. I know it's very common not to belittle your experience and your struggle, but it is very common to be confused when we go to semi-regular polyhedra. But we have a ton of time to figure all this out. So a prism, there you get the prism in like the crystal one with this light spectrum that is also called a prism. But in math, a prism is a three-dimensional shape that has a base. Let's pick a square as the base. Oh, that's an ugly square. I need to work on my freehand drawing. So let's say a square base. For example, you pick one, any polygon. And then vertical sides that go perpendicular up from that base. always perpendicular, 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 perpendicular. And then the same, this is a very ugly drawing, the same shape. Whoa, no artistic freedom here. The same shape as the base at the top as well. And there is my cube. Square base and the same polygon at the top. Perpendicular sides. Base at the top, same shape. Sorry, base at the bottom, same shape at the top. And a square prism is the same as a cube. So I put the I put the name of the polygon that is the base in front of the prism word because I can have many different prisms. They're not as easy to draw as the square, but I can have a triangular prism. That was a U. There you go. Triangular prism, where I start with a triangle. Now it doesn't have to be perfect. The triangle is going to be a little off like that maybe. I go all the way up, up, and up, perpendicular. Whoa! And then I have the same triangle shape at the top, and the side faces are also regular, so they in this case are squares. Triangle, triangle for the base and the top, and then the sides are always going to be squares. So I have my triangular prism. The word in front of the prism tells me what the shape of the base and the top is, and then the sides are always going to be square because they go perpendicular up, perpendicular, perpendicular, perpendicular. So this is a semi-regular polyhedron. It's a three-dimensional convex shape. It has regular polygons as its faces, more than one type. Let's practice here the faces, the vertices, and the edges. It's nice to be able to draw some basic prisms, yes, but just like for truncation, you just need to be able to understand what the shape looks like and be able to find the faces, the vertices, and the edges, and what kind of faces. So I always have two triangle faces in the triangular prism, two for the base and the top. And that's going to be in the name, triangular prism. So I'll have my two, plus now I have squares on the side, squares on the side. How many squares? Well, one for each edge of the triangle. So three squares on the side. So I'll have a total of five faces for the triangular prism. It's nice to be able to draw, well, the cube overlaps with the prism, so I can draw that already. But being able to draw a triangular prism is not the worst idea. It definitely helps me to find the faces, vertices, edges if I can visualize the shape. And a drawing helps that for sure. Is everyone happy with five faces? So we just need to understand what makes it a prism. Base, same shape at the top. So those are already two faces and always two. And then squares along the side. How many squares? Well, it depends on what the base is. For each edge of the base, there's a side wall up, and that wall is a square. Then the vertices. Well, the vertices will always be 2 times the number of vertices of the base polygon because there's a base at the top. I have vertex, 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 and at the bottom, and at the top, vertex, vertex, vertex. So 2 times 3 because the base was a triangle, and I have 6 vertices. Edges, I could not care less. To count these, I use Euler's formula. And on the left, for the faces plus the vertices, I have 11. So that means the edges must be 9. Now in the simple prism, I can definitely count them and see there are 3 groups of 3, but there's no need for that. The formula will help me when things get more complicated. Any questions on the triangular prism and where we get those numbers? It's a different kind of polyhedron, still semi-regular. So I need to understand what is the key feature of the prism to be able to calculate the faces, vertices, edges. But the name of the base is in the name, or oops, rather the type of polygon that is the base of the prism is in the name, and everything is connected to that. So the good news is I don't feel prisms are complicated in comparison to the other things we have introduced. It's a fairly familiar shape and one of the first ones for three-dimensional shapes in elementary school. The bad news is there are infinitely many of them because the base can be any regular polygon. And there's no limit to how many sides the polygon can have. So I have infinitely many of these prisms. Here, for example, is the hexagonal prism with a hexagon at the base. All the sides go straight up after that, so square walls around it, and then a hexagon at the top as well. So there are many prisms. Every different base is going to create a different prism. So there are infinitely many of these. Now we're not going to make the base polygon too big, but that is certainly possible. So these are the regular prisms.
So
What
can
we,
I ask just
yeah, yeah,
quickly? So the bottom and the top are always going to be two regular polygons, and then sides are always going
always
to
squares, yes.
always okay. Gotcha. So it's just always going to be two plus whatever the square number is around.
Yes, and the specific bottom and top polygon will be in the name.
Okay. Cool.
Then to go one step further, which is our last step, so deep cleansing breaths, though prisms feel a little better, I hope, we have the antiprisms. So what is happening, before I show the picture, what is going to happen is I'm going to take the prism and I'm just going to deform it a little bit. And by doing that, I'm going to create a new shape. So I'm going to take this hexagonal prism, for example, with a hexagon base, and all I'm going to do is pretend it's a rubbery material. I'm going to keep the base fixed, and I'm just going to twist the top face, rotate it slightly, so that these original top vertices now sit a little off center and across from the edges of the base. And when I do that, I change the side squares to triangles. So see how the bottom hexagon and the top hexagon, the top one is a little bit rotated to sit a little bit off center. Its vertices are now above the edges of the base. And in order for me to still have this roundish polyhedron shape and properties, I I have to split the original square. When I twist it, the square becomes two triangles, and I get this drum-like shape. Though I can again have any base polygon to start with. So these antiprisms are very closely connected to the regular prisms. They still have a bottom and a top that's in the name. So this will be the hexagonal antiprism. It's telling me there's a hexagon at the bottom and the top. And then the sides, instead of the original 6 squares over here, original 6 squares, when I do this twisting deformation, each square becomes two triangles. So the faces, let's just go back. The faces of the regular prism was a hexagon top and bottom and 6 squares on the sides because each hexagon side has a wall up. The the faces of the hexagonal antiprism is very much the same in terms of my hexagon bottom, hexagon top, but instead of the 6 original side squares, I now have 12 side triangles. Each square splits into two triangles when I do this kind of deformation. So the only thing, just like before, this one's much more difficult to draw. That's not my goal. The only thing is to understand what is happening around a vertex. And by understanding the prism, I can build from that and understand that I'm twisting the top face to create triangle sides instead of the original squares in the regular prism. And then I can see a vertex. I can count the faces. Let's actually do it for the hexagonal prism. We have how many faces? Let's jump back and forth. Faces, vertices, and edges for this hexagonal prism. So drawing it is not, whoops, not the goal. It's going to be a mess. I want to imagine it and find those numbers. Hexagonal anti-prism. Well, again, first, it's built on the prism. So first, understand the prism with the same base. That has faces, vertices, and edges. Now you're welcome to draw it, but I can imagine a prism fairly well. It's a fairly simple shape. So my faces will be two hexagons, because that's the base at the top and the bottom, plus 6 squares along the side, because of the hexagon. They have walls up, 6 of them on for either side. So I have 8 faces. The number of vertices, it's always 2 times the base shape because that shape is at the top and the bottom. So 2 times 6 is 12. Edges, I'm not going to bother counting them. I look at Euler's formula. The left side is going to be 20, so the edges are 18. Everyone happy with how we get faces, vertices, edges for the hexagonal prism? And we need that before we can deform it, just like we needed to know the platonic solid before we altered it to make the truncation. Now, not them, maybe just then, we can look at the corresponding same base, antiprism. Now all I need to know is how it changes. Don't have to imagine it perfectly, but I imagine sort of a rubbery shape where I take the top face, which is a hexagon, and I just twist it a little bit. In doing that, I still have my original two hexagons. Whoops, that's a hexagon like that. There we go. Two. Now, instead of the original 6 squares, I now have 12 triangles. Each square splits into 2 triangles. So I have 14 faces. And if we want to imagine it, it's over here. 14 faces. But counting the faces, I can easily miss one. So I'd rather understand how the prism changes to make this shape. And the only thing that changes in terms of the faces is each original square here splits into 2 triangles when I do this top twisting. It will always, the squares split in two. So I still have my top and bottom 2 hexagons. So the faces, the original 8 don't double, only the sides, the 6 square sides double to 12 side triangles, if you will. Let me just check when oh, sure, she got it. Okay. So it's not the original number of faces that double, it's the side faces that double. I still have my original top and bottom two. Now for the vertices, what has changed when I look at the pictures? From the regular prism, I had my top vertices 6, bottom vertices 6. What has changed in terms of the vertices? Nothing has changed. I still have my top 6 and my bottom 6. The fact that they're twisted a little bit doesn't change how many there are. So for the antiprism, the vertices don't change at all. The twisting action, if you can call it that, changed the faces and the edges, but not the vertices. So that's good news. So the vertices, exactly the same, still 2 times my original 6 because of hexagons, so still 12. If you're getting a little overwhelmed, this is the last one we are doing. It's the last of the 3 subgroups of semi-regular polyhedra. Archimedean solids, regular prisms, regular antiprisms. Faces plus vertices will now be 26, and therefore the number of edges will be 24, which you're welcome to go and count, but it's not necessary to have a perfect diagram, definitely not for the edges. Just by understanding what is the antiprism built on, what is it coming from, that means I have to understand that original shape first, understand how it's deformed and changed to get my new numbers. That is the end of my three-dimensional geometry chapter. Are there any questions that you would like to ask now before I switch it to our office hours, let's say?
So do we only need to know those, or we're only going to go through those two cube and tetrahedron truncated?
Okay, yeah, so let's
Um,
let's go through what we need to know for the test for sure.
okay.
Whoops. Space, I have space over here. Okay. Test questions. Let's be clear on that so it's on camera. In the catch-up sessions after this, we do whatever you want to do. So now, okay, so test questions. Let's just go to our table of contents here. Oh, I don't have the book. I have to open the book. Hold on. Let me just open the book to cover our quiz and everything. Let me just find my book here. Okay, so for quiz number 4, we have a page on tessellations where we've already said what those questions can be. What were those questions? Do you know the regular tessellations? How many there are? Vertex figure names, everything about them. Do you know some semi-regular tessellations? You don't have to know all 8 of them. Can you maybe draw one that has a square in it, or an octagon, or a square and a triangle, or something basic? And can you calculate all the interior angles of a regular polygon? Those were our 3 questions for plane tessellations. And we can, of course, go over that again in a catch-up session. Trigonometry, angle unit conversion, and a word problem involving a trigonometric function. That's page 2. Polyhedra is where what we just did. There will be 2 pages on that. One page is on platonic solids. Do you know everything about the platonic solid? The faces, the vertices, the edges, the vertex figure name? Can you draw it? All those things. Those we do want to draw. The next page is on the other polyhedra. Can you find faces, vertices, edges of a truncated platonic solid? Or a regular prism? Or a regular antiprism? How many Archimedean solids are there? And can you name one? And that's it. Well, there's another page, but that's the next chapter. I went fast because I am recording it, and you can just watch that over and over and over. And I can repeat that in the next session as well. So we've covered 4 pages so far with area and volume calculations for 3-dimensional shapes being our last chapter. But I think the best thing to do moving forward, let's look at our calendar here. Calendar, where are you? Calendar, we're at the 30th. Our quiz is on the 8th. So what we can do is definitely take tomorrow for 9:30 to 11:30 is bring your own questions. You tell me what you want me to do, catch up day, and then we'll reassess how if we need another one for Wednesday or we want to get chapter 17 done and then have a bunch of catch ups. But let's have a catch up day tomorrow at least, and then we will reassess where we are at, in addition to the next hour, of course. So let me just end the video, but I'm still in Discord, of course.